can see it.
Perfect.
And
Just
you have, yeah, we have, let me see that, 25 minutes roughly for the talk.
yes, exactly.
All right.
Okay, thank you. So, hi everyone. I will talk about the track reconstruction of free streaming data at PANDA at FAIR, and I will put an emphasis on the quality assurance for this data. And yeah, my outline you can see here, it's the following. I will first discuss the PANDA detector, then I get to the time-based data stream and the time-based clusterization also that we are using. Finally, I get to the quality assurance and my results. So first of all, PANDA, that stands for antiproton annihilation at Darmstadt. And you can see the detector here. We will use a stored antiproton beam. You can see that in the figure coming in from the left. And we will use a beam momentum ranging between 1.5 and 15 GeV per C. And we will also use a internal proton target. You can see that in the figure here being dropped from above. And what's important for the time-based data stream is that there will be a quasi-continuous beam used, so antiproton beam. And I want to show some more details from the detector. So in order to fulfill the physics requirements, PANDA will be an almost full 4-pi detector. And it will be divided into two parts. So the target spectrometer marked in blue in the figure and the forward spectrometer marked in yellow in the figure. And the main tracking detectors is closest to the interaction point. We will use a microvertex detector. Outside of this one, we will have the straw tube tracker, which I will introduce a bit more in detail. And going into the more forward direction, since it's a fixed target experiment, we need to cover those angles quite in detail. So there we will use gas electron multiplier stations and also forward tracking stations. The tracking, we will have both online and offline tracking, and we will mainly have less than 10 tracks per event. And we will use the usual things, vertexing, particle identification, and calorimetry. For the readout, which is important for the work I will discuss, here I can mention that the average interaction rate at later stages of PANDA, what we refer to as the phase 2 or the full luminosity phase, that will be around 20 megahertz. And in earlier stages, phase 1, we refer that to, the interaction rate will be about 10 times lower, so about 2 megahertz. And this is the range where I will be focusing, so the lower interaction rates. We will use continuous readout. And the reason for this is that the background and signal are quite similar. And so we will not use a hardware trigger. And we'll use fully software-based event filtering. And here the tracking information will be used in order to decide which data to keep. And my work focuses mostly on the straw tube tracker. And here you see a picture of that. And it will consist of roughly 4,200 closely packed single channel readout drift tubes. And if we zoom in a little bit more to the detector, we can also see how the layers are placed in relation to each other. So we will have about 19 radial layers for XY reconstruction. Those are marked in green in this picture. And we will have 8 layers of tilted tubes with plus minus 3 degrees for the Z reconstruction. These are the red and the blue tubes. What's important also for the track reconstruction in this detector is that we will use drift circles. And this is the circle which has the center in the tube center, and the track goes through this circle, and you get this from the minimum drift time of the electrons in the straw tube. You also see the dimensions of the tubes here. Something that's important for the work is that the maximum drift time of the electrons in the straw tube tracker is 250 nanoseconds for the ones originating from close to the tube wall. And also important is the structure of the beam in the high energy storage ring, which is the storage ring where PANDA will be placed. So the storage ring will be about 80% filled with antiprotons, and we'll have 2000 nanoseconds revolution time, which gives you a 1600 nanosecond beam with a 400 nanosecond gap. And so this creates natural data bunches of about 2000 nanoseconds. However, we will also have event mixing in these data bunches, and this you can see on the figure to the left. So here I show a plot of the time between the start of 2 consecutive events at 2 megahertz interaction rate. There, the average, of course, between 2 events is 500 nanoseconds. And you can see that most of the events occur much closer in time than the 500 nanoseconds. So, of course, within the 2000 nanoseconds, we will have event mixing. So we need to disentangle these tracks belonging to different events. And the way this can look in the straw tube tracker, which have a timing resolution of the order of 100 nanoseconds, is in the following way. Here I show the event structure, so the timestamps versus just the total number for 0.5 and 4 megahertz interaction rate. And you can see that at the lower interaction rate here, the events are clearly separated. You basically don't have any overlapping between the events, but already at 4 megahertz, there the events start overlapping, so it can get quite tough disentangling these. And however, since the beam is quasi-continuous, then we will also have event mixing at the lower interaction rates as well. And now I want to compare the event sorted versus the time sorted data, because what's new now is that we can perform the track reconstruction on time sorted data. So as I display in these figures, you see when we do the simulation event sorted data, then of course at the simulation stage, all points are ordered event by event, and also at the digitization stage and at the reconstruction stage. So there you already have the events clearly separated, and the data is synchronous all the way between the simulation and the reconstruction state. And from there, the data is also synchronized going to the analysis level. However, if you use time sorted data, this looks the same at the simulation stage. Everything is ordered event by event. However, at the digitization stage, here we resort all the digits, so the digitized hits in time, and then we group them into different intervals. And these intervals can, for example, be chosen to be 2000 nanoseconds, which is what I chose for the results that I will show soon. And yeah, so now you see that already at the digitization stage, the data will not be synchronous with the simulation anymore. And here we will also have some digits in between the events. And one can also mention we have no prior knowledge at this stage where from which event one digi came from. But of course, from the Monte Carlo truth matching, we have that, but not for doing the realistic track reconstruction. And as a result of this, then of course the tracks, when you have reconstructed them time sorted digits, they will also not be synchronous with the events, but they will occur in different track candidates, or even as event candidates if you perform the event building simultaneously, and they will be placed within these bunches or bursts, as we call them. And the data from this stage will be sent on to the software trigger or to the analysis stage, and to the analysis stage after the trigger. So they will also be asynchronous with the simulation stage, but they will be synchronous from the reconstruction stage. And this is how the event mixing will look like in the actual StrawTube tracker. So here you can see a comparison between when we do a track reconstruction on one event at a time, or if we have some level of event mixing. So you see, if we have only one event, then yeah, it's easy to, or not easy, but it looks quite straightforward to perform the tracking, and we can almost map out the tracks by eye. However, this is really, it looks really messy when we have event mixing. So one possibility to disentangle these tracks when event mixing occurs is to use 4-dimensional tracking. And that I illustrate here, how we are doing this. And so the most evolved track reconstruction algorithm for running on time-based data right now for PANDA is based on the cellular automaton. And the algorithm works in the following way. In figure A, you can see two particles, or the tracks from two particles which have traversed the StrawTube tracker. In figure B, these tubes are numbered, and the red tubes illustrate ambiguous hits. So these are hit tubes which have more than 2 fired spatial neighbors, and the green ones are tubes which have at most 2 neighbors, and these are referred to as unambiguous. And all the tubes which have fired are iteratively renumbered until they have the lowest possible number within the entire bunch or within its neighborhood. So this is illustrated in figure C. And the ambiguous hits are given all numbers possible, and they are dealt with at a later stage after a track reconstruction have also, or sorry, after a track have been fitted to the clustered hits. And the reason why we are focusing on this algorithm is that it have 2 advantages. One is that it's parallelizable, so it's implemented on the GPUs, and therefore it's a candidate for online usage. It also doesn't use the interaction point as a constraint, so it's suitable for reconstructing secondary tracks. And I should mention that in the real experiment, this will be used together with a primary track finder, so one which uses the interaction point as a constraint. But the results I will show now is for this algorithm only. And at least 3 StrawTube tracker hits are required, of course, to fit the circle. And in the 4-dimensional tracking, which I mentioned, there we add the timing constraint of the hits. So 2 hits can only be combined if the timestamps differ less than 250 nanoseconds or a certain set value. And I will show how the reconstruction efficiency depends on this value. And so in order to discuss the results, I first want to discuss a bit more in detail the quality assurance. So of course we need to do quality assurance for the tracking algorithms to know how well they work. And the one we are using in PANDA gives us the momentum resolutions, the number of true, false, and missing hits per track in the different detectors. And it also gives you different track categories. And these I will show a bit more about. And in order to give a fair representation of a tracking algorithm, we of course only want to compare to tracks which could be reconstructed in the relevant detectors. So for this we use a reference track set, and these are all the ideally reconstructed tracks with a certain hit requirement. And in the definitions I will be using, a true Monte Carlo track is defined as the one which gave rise to the majority of the hits in the reconstructed track. And the track categories are the following. So we have 4 track categories of correctly reconstructed tracks. These are the fully purely found, where we have found all the true hits in one Monte Carlo track. And we also have fully impurely found, where we have found all the Monte Carlo hits from one Monte Carlo track, but impurities are allowed. So you can have an additional 30% of hits from another Monte Carlo track. And we also have partially purely found, where the majority of all hits belong to a Monte Carlo track. So not all hits were found, but you don't have impurities from other tracks. And the last category is partially impurely found, where we have found at least 70% of all the hits from one true Monte Carlo track, but not all of them, and the impurities are allowed here. I can also mention that you cannot have one track belonging to more than one of these categories. And then we also have 2 categories of falsely reconstructed tracks. These are ghost tracks, which do not fulfill the requirement to correspond to a single Monte Carlo track. And we also have clones, where one track was found more than once. And here I show you the efficiencies. So I show it for 2 different cases, one for the 3-dimensional algorithm and one for the 4-dimensional algorithm, where I use the timestamps. And you can see the different track categories as well, and the interaction rates differ between 0.5 to 4 megahertz. And you can see that in both cases, the efficiency is quite stable over the relevant range of interactions, but it's more stable when you use the timestamps, so in the 4-dimensional case. And you can see that at lower interaction rates, the 2 cases, they coincide quite well. And I should also mention how the efficiency is defined. So that's the number of found tracks over the number of possible tracks for each category. And of course, one also have to state the fake rate of the algorithm, and this I show here for the ghost rate and the clone rate defined in the way you see in the box. And in the same plot here, you see the cases for both the 3-dimensional and the 4-dimensional tracking. And you can see a similar pattern here, that the 2 cases coincide quite a lot at the lower interaction rates, but they part at the higher interaction rates. And you can also see that including the timestamps at higher interaction rates actually lowers the fake rate quite a bit. However, at all interaction rates, we have quite high fake rates, and the reason for this is that we have not yet included a ghost or clone cleanup procedure. This is the next step in this development. And I also want to show the efficiencies as a function of the time cut. So here I do the time-based reconstruction at 2 megahertz. I keep it there, and you can see the efficiency and the fake rate as a function of the time cut. And I've also marked here the maximum electron drift time, so the time cut I was using in the previous slides. And you can see that if one uses a, if one constrains the time cut and lowers it, then it decreases the efficiency a little bit, and it greatly decreases the fake rate. However, if we loosen the time cut and allow in more hits within a bigger time span, it doesn't affect the rates so much in either of the cases. And yes, so one can see that by including the timestamps, one can greatly reduce the fake rate here. And since we want to use this algorithm online, we have of course also looked at the runtimes of the algorithms. So here I show 2 cases. One is where I compare the runtime of the algorithm, so the time it takes to establish the neighborhood relations for the 3-dimensional case where the data is processed event by event, and for the 4-dimensional case where the data is also processed event by event. And in the figure here, it looks like quite a big difference because of the scale. But if one compares the difference between the 2 different cases to the full runtime, which is 10 milliseconds on an Intel 7 processor, then you can see that it's only about 1% difference in the runtime. So it's not much at all, including the timestamps. And I also show here the time it takes processing the data bunches. So the lines here to the left, they correspond to the processing time per event. But in the graph, it's the processing time per bunch. And you can see that at the lower interaction rates, we have a slightly lower processing time than at the higher interaction rates, but it's not a huge increase here either. But as expected, it does, of course, it does increase a little bit. Yes, and now I already come to the summary. So the most important part here is that timing information is included in the cellular automaton-based hit clusterization, and also that the algorithm can now accept time-sorted hit data. And we also see from the results that the efficiency is stable over the interaction rates, corresponding to 0.5 to 4 megahertz, which is corresponds to the start setup of PANDA. And one important finding is also that the timestamp utilization greatly suppresses the fake rate at higher interaction rates, and also if you tighten the timestamp. And yes, we also see no significant slowdown in the runtime when using the timestamps. And the outlook, as I already mentioned, we need a clone merger and a ghost cleanup procedure to take care of the fake rate. And this was all for me. And if you have any questions, I'm happy to answer. Thank you.
Thank you very much for the very nice talk. We have time for a few questions before we go to the next talk.
Hi, very interesting presentation. Can I ask my question? Sorry, I didn't raise my hand.
That's okay.
you showed the improvements in time, but I didn't get a good understanding of how good the time resolution is. Of course, you have the detector that you have, but how far apart in time? I didn't see the distributions in time of the hits, and then your time resolution. How much is your resolution compared to that natural spread?
So the resolution of the timing signal we will get from the stereotube tracker is about 70 nanoseconds. So that's what we have to work with.
And how big is the spread of the time of the hits, just if you look at the total time distribution?
Yes, so right now we are, so the spread of the timestamps within one track is usually about 100 nanoseconds around there. So this timing information is mostly usable when we have event mixing. So it's not, we cannot use it within one event because there the timing resolution is not enough. So we can use it for separating the events when we have a couple of 100 nanoseconds apart.
Okay, thank you.
I had just a quick general question. You mentioned also that you have 2 tracking passes, like the one including the primary vertex constraint.
Yes.
Is one of them meant to be online, offline more, or are they going to run in parallel, or they target different things?
Yes, so what I showed the results from now is from the secondary tracker, and this one is, we're aiming to use this one online since it's parallelizable with the cellular automaton, but we also have several primary track finders, and there we need to find which is the best one now to use together with the cellular automaton. So we are aiming to use this one after having run a primary track finder, as I said or showed here, but I don't think I said it, that the track reconstruction now is performed without a pre-processing event building, and also not with a primary track finder before. Okay. But yeah, that we have to investigate which is the most suitable primary track finder. But this is for sure one of the most promising secondary ones.
Okay. All right. One more last question before we move on.
So I have a very quick question.
Yeah.
Andy here. Do you have, so you said you have duplicate tracks as well, but is it also like looping particles which go into your next time window? And how do you deal with that?
Yes, so one of the reasons why we get quite a lot of duplicate particles is because of the structure of the stereotube tracker here. It's when we tend to, for some reason, miss hits in the skewed layers here, the blue and red ones. It is the curling tracks. Yes, we do have quite a lot of them in these type of events. So this is for minimum bias events, the results I showed. But they will not go into a new time window because still at the lowest momentum the particles can have, even when they spiral in the detector, they are still so fast that they do not come into a new time window. But we have all the hits from one track will be within 100 to 200 nanoseconds, definitely.
Okay. So yeah, I'm of course always thinking in LHC timing terms. So, but then you have them within one event, and you will have to reconstruct loopers there, right?
Yes, that we will need to take care of. So this is definitely a big part of the of the fake tracks that we get, that the track finder is missing some of this.
Thanks, Jenny.
Thank you.
All right. Thank you very much. So I hope we continue the discussions also in, I guess, next Monday's, was it? I can't remember. One of next week's discussion sessions. Don't quote me on Monday. All right, then we move on to the next talk, which is by Patrick.
Yes. Can you hear me?
We can hear you, I think.
Great. Yeah, I need, yeah.
So I think when, yeah.
The sharing to stop.
Yes. Let me